Every single hour, more energy from the sun hits the Earth than the entire human race uses in a year. Yet, for decades, we've been trapped by a mathematical ceiling that says we can only capture a tiny fraction of it. This isn't a failure of our manufacturing or our engineering. It's a fundamental rule of the universe called the Shockley-Queisser limit, which dictates that a standard solar cell can never be more than about 33% efficient. But in March 2026, researchers at Kyushu University did something that shouldn't be possible. They didn't just nudge that limit, they shattered it, using a metal you've probably never thought about, molybdenum. To understand why this matters, we have to look at how a normal solar cell works. Think of a photon like a single ball being thrown at a target. In a standard cell, one ball can only knock loose one electron. If that photon has too much energy, the extra is simply wasted as heat. It's like throwing a bowling ball to knock over a single plastic pin. All that extra momentum just vibrates the floor and disappears. This heat is the enemy of efficiency. It degrades the hardware and limits the power output, creating a bottleneck that has defined the solar industry for over 60 years. Until now. The Kyushu team realized that to beat the limit, they needed a way to turn that wasted energy into more electricity. They needed a process that could turn one photon into two excitons. This is the holy grail of photonics. If you can double the output of every high-energy photon, the theoretical efficiency doesn't just go up, it jumps past 100% for specific wavelengths of light. But doing this in a stable, reliable way has been impossible. The molecular timing required is so precise that even the slightest misalignment causes the whole process to collapse in less than a nanosecond. The secret weapon turned out to be a specific arrangement of molybdenum-based emitters. Molybdenum is a transition metal often used in high-strength steel, but here, its electronic structure provides a unique shortcut. Unlike the organic molecules previously used for this process, molybdenum is rugged. It can handle the intense energy transfer without breaking down, acting as a perfect bridge for the energy to cross. By precisely tuning the distance between these molybdenum atoms, the researchers created a spin-flip environment where energy could be divided and conquered with unprecedented speed. This is where the 130% figure comes from. It's called external quantum efficiency. For every 100 photons of a certain color hitting the surface, the device generates 130 excitons. It's literally more than the sum of its parts. It sounds like magic, but it's just brilliant engineering. By using molybdenum to manage the spin of electrons, they've found a way to bypass the thermal waste that has plagued solar energy for a lifetime. But how do you actually flip the spin of an electron on a nanosecond timescale? To understand that, we have to go deeper into the quantum engine at the heart of this emitter. In the world of quantum mechanics, electrons have a property called spin. Think of it like a tiny internal compass. Usually, electrons like to exist in pairs with opposite spins, one up, one down. When a photon hits a molecule, it kicks an electron into a higher energy state called a singlet. In this state, the spins are still paired, but the energy is unstable. It wants to escape, usually as heat. The Kyushu team's molybdenum emitter changes the rules. It forces one of those spins to flip, turning the high-energy singlet into two lower-energy triplet states. This is the spin flip that makes everything possible. This process is called singlet fission. Imagine you have a $100 bill, but you can only spend it at a store that doesn't give change. If you buy a $40 item, you lose $60. That's a standard solar cell. Singlet fission is like having a machine that instantly swaps your $100 bill for two $50 bills before you walk into the store. Now you can buy two items and lose almost nothing. You've doubled your purchasing power. In the molybdenum emitter, this happens with incredible efficiency. Because molybdenum atoms are heavy and have a high spin-orbit coupling, they act like a high-speed gearbox for these electron spins. But there's a catch. For singlet fission to work, the molecules have to be aligned with sub-nanometer precision. If they are too far apart, the energy can't jump. If they are too close, they quench each other and the energy dies. The Kyushu researchers solved this by using a self-assembling molecular framework. They designed the molybdenum molecules to naturally lock into the perfect orientation, like a set of high-tech Lego bricks that find each other in the dark. This alignment is what prevents nanosecond timing failures. By fixing the geometry, they ensure the spin flip happens in picoseconds, faster than the energy can ever turn into heat. Once the energy is split into two triplets, it needs to move. These excitons, essentially packets of energy, have to travel through the material to the electrodes to become actual electricity. Molybdenum's unique crystalline structure creates a superhighway for these excitons. They can travel much further than they could in traditional organic materials, meaning we can make the solar cells thicker and more durable. This durability is key. Most high-efficiency lab experiments fall apart when you take them outside, but molybdenum is a workhorse metal. It doesn't care about UV light or oxygen. It just keeps flippin' spins. The result is an emitter that doesn't just work in a clean room. It's the first time we've seen 130% quantum efficiency in a material that could actually survive on your roof for 20 years. By combining the buy one, get one free physics of singlet fission with the industrial strength of molybdenum, the Kyushu team has built the engine for a new era of energy. But the implications go far beyond just better solar panels. If we can manipulate electron spin this easily, we can change how almost everything works, from the lights in your home to the sensors in your car. When we talk about revolutionary tech, there's usually a catch. It requires a rare, expensive element, like iridium or platinum. But molybdenum is different. It's the 54th most abundant element in the Earth's crust. We already mine over 200,000 tons of it every year. We use it in everything from engine parts to bicycle frames. This means the supply chain for a molybdenum energy revolution already exists. We aren't waiting for a new mining industry to be born. We're just taking a material we already understand and giving it a massive quantum mechanical upgrade. The industrial potential here is staggering because these molybdenum emitters can be applied as a thin film. They can be printed onto existing solar cells to give them a massive boost. Imagine a world where upgrading a solar farm doesn't mean replacing the panels, but simply applying a new layer that instantly breaks the 100% theoretical limit. It's a software update for hardware. This scalability is what makes the Kyushu discovery so dangerous to the status quo. It's not just a lab curiosity. It's a manufacturing blueprint. And it's not just about taking energy in. These same molybdenum emitters work in reverse. They can be used to create hyper-efficient LEDs that produce almost no heat. In a standard LED, a lot of energy is lost as heat, which is why your phone gets hot when the screen is on. But with spin flip technology, we can create light with nearly 100% internal efficiency. This would double the battery life of our devices and allow for displays that are brighter than anything we've ever seen, all while using a fraction of the power. The 130% efficiency of the Kyushu emitter is just the beginning. Now that we know how to use molybdenum to manipulate excitons, we can start looking for even more complex spin states. We are entering an era where we don't just accept the limits of physics, we engineer our way around them. The Shockley-Queisser limit was a wall, but molybdenum is the door. By mastering the nanosecond dance of the spin flip, we've turned a common industrial metal into the key to a sustainable, high-energy future. Next time you see a solar panel or look at the screen on your phone, remember that underneath the surface, there's a quantum world we are finally learning to control. The engineering required to make this work is staggering, but the result is simple. More energy, less waste, and a world that runs on the very same physics that powers the stars. The 100% limit is gone, and the future of energy is finally looking as bright as the sun itself.